Hello.
Scooby-Doo, looking for you. Scooby-Doo, where are you? All the stars are here, waiting for you. Couldn't have a show without you.
Hello, hope you're doing well today. I want to talk about several types of factoring techniques of what we call special products. We'll talk about several. One is the perfect square trinomial. So if you see, notice this is a trinomial because it has three terms, something squared, and then 2 times AB, and then B squared. So if you find a trinomial that's of that format, it factors into A plus B times A plus B. But now I want to talk about this from a different point of view. If you watched the last video, you would consider this a trinomial with a leading coefficient not equal to 1, right? It's 100. So a method for doing that is we use the AC method where we multiplied 100 times 9 and we find numbers that multiply to be 100 times 9, which is 900, and also add to be the middle number, which is 60. You might have to think about that for a minute, but when you exhaust all the possibilities, the numbers that multiply to be 900 and add to be 60 is 30 and 30, because 30 times 30 is 900 and 30 plus 30 is 60. Your next step was to rewrite your middle term. So this term right here, 60x, we're going to replace it with 30x and 30x. So now we have 100x squared plus 30x plus 30x plus 9. And then you do factor by grouping. So when I look at the first two together only, I ignore the last two terms, I pull out the greatest common factor, which looks to me is going to be 10x. And if I divide 100x squared by 10x, that's going to give me 10x. And if I divide 30x by 10x, that's going to give me plus 3. And over here, these guys have a factor of 3 in common. So I pull out the positive 3, and that's going to give me 10x plus 3. Remember, the idea is what's in parentheses must match, so my answer is 10x plus 3, which is the one that matches, times what's left out front, which is also 10x plus 3. Now, it turns out that if we would have recognized at the beginning that this first guy right here, let me use a different color here. This first guy right here is a perfect square. The square root of 100x squared is 10x. And also, this guy down here is a perfect square. The square root of 9 is 3. But also, the middle has to be 2 times the square root of each of those. So again, the square root of 100x squared is 10x. The square root of 9 is 3. And if we do 2 times those two guys multiplied together and get the middle, so 10x times 3 is 30x times 2 is 60x, it checks out, then my answer is just the square root of each of them, okay, times itself, okay? So notice that would take me straight to, A is 10x plus B is 3 times 10x plus 3. Now what I want to point out is this method works just fine. We didn't have to learn a new method to solve this, to factor this problem. We already have a method for factoring this problem, so don't feel like you have to learn the perfect square trinomials rule. On the other hand, it can make your life a lot easier. So let's check this out. Let's look at it here. The square root of 16y squared is 4y, right? The square root of 9 is 3. So what we know is that we don't know if this will work, but we know it's a possibility. If you multiply those two together times 2, so 4y times 3 is 12y times 2, that is 24y, which means this problem directly factors into 4y plus 3 times 4y plus 3. You could also write that as 4y plus 3 squared. Either one of those is correct. So if you recognize the type, you go right ahead, try it out. But if you don't, all the methods that you already know how to use from the last section still apply to these trinomials. So question is, on this problem, will it work? So the square root of 9x squared is 3x. The square root of 4 is 2. If I multiply those together, I get 6x, and double it, I get 12x. Well, sure enough then, that means my answer is 3x plus 2 times 3x plus 2. But now I want you to realize, if we look at it the other way, and I'm not going to do them all both ways, but it's good practice to see if the AC method will work. 9 times 4 is 36, so we're trying to find numbers that multiply to be 36 and add to be the middle number, which is 12. Well, we know that's 6 and 6, right? So I rewrite my problem as 9x squared plus 6x plus 6x plus 4. Factor by grouping. What comes out of here is a 3x. That leaves me with 3x plus 2. What comes out of here is a 2. That leaves me with 3x plus 2. And there I am in the same place. That's 3x plus 2 times 3x plus 2. It doesn't matter to me which method you use as long as you're getting your problem right. Okay? Now if I look at this, I don't even need the AC method to do this. What multiplies to be 9 and adds to be negative 6? Well, that's negative 3 and negative 3, right? Or I could try this method that we just did, and this is a perfect square. The square root of that is z. 9 is a perfect square. The square root of that is 3. If I double these multiplied together, well, these multiplied together is 3z. Doubled is negative 3z, right? Well, I'm sorry, it's 6z, right? So you're supposed to say, no, it's not right. 3z doubled is 6z. Well, what about the minus? Well, the minus has to go with the 3, because when you take the square root of 9, it could be 3 or negative 3. So anytime this term is negative, you're going to have z minus 3 times z minus 3. Or again, what multiplies to be 9 adds to be negative 6. That gets you there too. So let's look at the last one on this page. Does it fit the mold? 25y squared, the square root of that is 5y. 64, the square root of that is 8. If I multiply these together and double it, well, 5y times 8 is 40y, doubled is 80. But what about the negative? Well, that means we're subtracting, right? So my answer is going to be 5y minus 8 times 5y minus 8. Now, how could we really check this to see if it's right? You know what to do, right? Well, multiply it out. 5y times 5y is 25y squared. 5y times negative 8 is negative 40y. Negative 8 times 5y is negative 40y. Negative 8 times negative 8 is plus 64. Then we combine like terms to get negative 80. Yep, we did it right. Now let's continue practicing in this method. The trick is really going to be recognizing that it's one of these problems. It's not that the method is hard. It's not. It's when you look at this trinomial, you go, oh, this is a perfect square problem. So 64m squared is 8m. 49n squared is 7n. Now if we multiply those together and double it, will that equal to 112? Well, 8 times 7 is 56. M times n is mn. Doubled is 112. So this will factor in, and look, that's plus, so that means our factors are plus. 8m plus 7n times 8m plus 7n. Again, the method is not hard. It's just you got to recognize it with it mixed in with all kinds of other problems as well. So the square root of 9u squared is 3u, right? The square root of 100 is 10. If I multiply those together and double it, so 3u times 10 is 30u doubled. Uh-oh, that doesn't give you 87u, right? So you know what? Does that mean it's not factorable? That means we got to try something else, okay? And it may not be factorable, but we've got to try the other method that we know. So this is a good lesson, and it doesn't always work out like you think it should, okay? So I'm going to get rid of this and try a different method. So this time, I'm looking for a greatest common factor. We don't have it. We're trying to find numbers that multiply to be 900 and add to be 87. So we might have to think for a minute and figure out what numbers multiply to be 900 and add to be 87. Now the first thing that gives me 900 is 90 and 10. That's not going to work, right? And we need to think smaller, like 900. What else would go in 900? Like 300 times 3. That's not going to work out either. And we can come up with a really big list. But I've got it. It's 75 and 12. Now, I didn't just, I went through a big list in my head to come up with that 75 and 12. So don't think that was my second guess. It wasn't. I had to work on it, and I just looked at a lot of options of multiplying to get 900, like 45 divides into 900, 60 divides into 900. I tried a lot of things and finally got 75 and 12. So now what I do is rewrite. Now when you can come up with those two numbers, that means your polynomial does factor. If those two numbers don't exist, that multiplies to b, the AC, and adds to b in the middle, that means your polynomial does not factor. Now I need something that divides into both 9 and 75. They both have a u in common. I believe 3u is the winner, so it's going to leave me with 3u plus 25. What goes into both 12 and u is actually 3. Not 3, I'm sorry, 4. 4. That's going to give me 3u plus 25. And remember, these have to match. If they don't, we did something wrong. So that's 3u plus 25 times 3u plus 4. And there we go. So that was not a special product. That was an AC method, and you could have also tried it by trial and error. So let's try a third one before we move on to something new. And this time is 27p squared q. No, that's not a perfect square. But look, every one of these has a q in it. And I do believe that at least 3 divides into all of these. So let's pull out a greatest common factor of 3q. Remember, that's the first step of every problem, is to see if there's a greatest common factor. And if it is, pull it out. So if I divide this first term by 3q, well, 3 divides into 27 9 times, and there's still a p squared there. I divide 90 by 3, that's going to be plus 30, and then the q comes out, there's a p, and then I divide 3 into 75, that's 25, and the q comes out, and that leaves that. Now the question is, hey, does this fit that category? The square root of 9p squared is 3p, the square root of 25 is 5. If I multiply these together and double it, will that give me 30p? And it will, because 3p times 5 is 15p. 15p doubled, or times 2, is 30p. So that means don't forget about your greatest common factor in the front. And then we have 2 sets of parentheses with 3p plus 5 and 3p plus 5. And that is completely factored. Now let's take a look at a second technique. This is called a difference of squares. And if you'll look at your rule, notice we have a binomial this time. We have a squared minus b squared. So if your first term's a perfect squared, your second term's a perfect squared, and also very important, it's a minus. That's what they call it, the difference of squares. Then your factors are a plus b times a minus b. So one positive, one negative, the square root of the first one in the first spot, the square root of the second one in the second spot. So let's see if that works. First of all, is it minus? Yes. Okay. Is this a perfect square? It is. Square root of that is 10x. Is this guy a perfect square? Sure is. Square root of that is 3. That means this factors into 10x plus 3 times 10x minus 3. Now, how could we check it? You know what to do. Multiply it out. So 10x times 10x is 100x squared. 10x times minus 3 is minus 30x. 3 times 10x is plus 30x. 3 times negative 3 is minus 9. Those cancel, and it checks out. So we know we did this correctly. Let's take a look at the next one. First of all, we're subtracting. That's required. If it's addition, you can't factor it. Only a difference of squares can be factored. So 6y squared, the square root of that is 4y. 9, the square root of that is 3. And again, we're subtracting. That means it factors into 4y plus 3 times 4y minus 3. So notice the square root of the first one goes in the first position of both binomials. The square root of the second one, 3, goes in the second position of both binomials. And we are finished with that problem. Let's keep going. Again, the challenge, on these, just like many other factoring problems, is actually recognizing the type of problem. Because you're going to be presented a test full or a homework full of all different types of problems at some point, and you're going to have to recognize the type. So I look at K and go, oh, that's a difference of squares. I have subtraction, good. The first term, the square root of that is 3x. The second term, the square root of that is 2. That means we've got this as 3x plus 2 times 3x minus 2. Okay. I look at z squared minus 9. Same idea. Z squared is a perfect square. The square root of that is z. 9 is a perfect square. The square root of that is 3. So my answer is z plus 3 times z minus 3. And by the way, it's perfectly okay to write it as z minus 3 times z plus 3. The order that you write your factors in, remember, doesn't matter. And that's the commutative property of multiplication. All right. Look at this m character down here. So, the square root of 25y squared, we know is 5y, right? The square root of 64 is 8. And again, please note that there's a subtraction here. You can't do it if it's addition. So this is going to be 5y plus 8 times 5y minus 8. And we're finished with that problem. All right, here we go again. 144p squared minus 9q squared. So the square root of 144p squared is 12p. The square root of 9q squared is 3q. And there's that all-important minus sign. So my answer is 12p plus 3q times 12p minus 3q. And we're finished. Now this next one is really interesting. I think you're going to like this one. The square root of x to the fourth we know is x squared, right? Because x squared times x squared is x to the fourth. The square root of the y to the fourth is y squared. So I have x squared plus y squared times x squared minus y squared. But there's a little something extra going on here. Look at this. These guys right here, perfect squares again, right? So the x squared plus y squared, I'm going to bring that down, and then we factor here into x plus y times x minus y. This is completely factored. So always check to make sure that your factors can't be factored again. Okay, so this is like a two-step problem going on. That x squared minus y squared could go again, but remember we talked about x squared plus y squared, a sum of squares, won't factor at all. So let's keep going. And lo and behold, look at there. I got a sum of squares, don't I? And I can't find a color I want to use. There we go. So I've got 36y squared. The square root of that is 6y. 81, the square root of that is 9. But here's my problem. I can't do anything because it's a sum of squares. This is not factorable. Another way you could say it is that it's prime. Be careful in your homework. Just make sure you follow the directions and you write whatever they want as far as not being able to do the problem. Alright, so let's talk about our final type of problem, which is a sum or difference of cubes. So a sum of cubes is that is a perfect cube plus a perfect cube. Sum meaning plus, okay. What you do is you take the cubed root of the first term, and it goes there. The cubed root of the second term, and it goes there. If your problem starts with a plus, then a plus goes in between. The next thing you do is you square the first term. So whatever you have here, you multiply it times itself, it goes there. You multiply these two guys together. Notice that goes there. And you change the sign. So whatever that goes there is the opposite. So you change. And then the last term is just the last term squared. So it's something to remember. It's probably the hardest formulas to remember as far as factoring goes. But the thing is, if you can recognize them, you can do this. And if you practice enough of them, it'll be fine. So first of all, when we look at this first problem, is it a sum of cubes? In other words, the cubed root of x to the third is x, so that's a perfect cube. What about the cubed root of 8? Is the cubed root of 8? So the cubed root of 8 is 2. Yep, so that's a perfect cube. So if I use this formula, then what I do first is I say x plus 2. The reason I put a plus is because it was a plus to start with, and I took the cube root of each of them. Now, the next set of parentheses is a longer set. It's got 3 terms in it. And what you do is you square the first one. So square x, okay, and then you multiply them together. Okay, so x times 2 is 2x, but whatever's here changes to the sign there. And then you square the last one, and it's always plus. So no matter what your original problem is, this is always positive. So always plus. Okay? Now let's look at another one. Notice this is another plus problem. And let's see if it'll even work. So the cubed root of the y to the third is y. What's the cubed root of 27? Well, 3 times 3 times 3 is 27, right? So the cubed root of 27 is 3. So remember, your first set of parentheses is the short set. And you just do each of the cube roots there with whatever you started with operation-wise. And then the second set of parentheses is where you've got to square things and multiply things together. So the first one's always the first one squared. So y squared goes there. If you have a plus here, you change the sign. You multiply these together, so that's 3y. And then you always put a plus and square the last one. 3 squared is 9. Now, here's what you don't have to worry about. This will not factor. When you get that trinomial from factoring a sum or difference of cubes, you don't have to worry about that trinomial factoring. It won't. You can try. What multiplies to be 9 and adds to be -3, don't think too long, because you're not going to come up with anything. Same thing with multiplies to be 4 and adds to be -2. Not going to happen. Right? Let's keep going, okay? The cubed root of x to the third is x. The cubed root of 1 is 1. But this is a difference of cubes. But you can still do it. You can factor for cubes, you can factor a sum or a difference of cubes. But for squares, you can only factor a difference of squares. So write that down somewhere. It's important. You can factor a sum or a difference of cubes, but you cannot factor a sum of squares. But here we go with this difference of cubes. I'm going to have x minus 1. So remember, the cube root of each of them goes in the spot. Whatever's here goes there. Then you square the first term. So that's x squared. You multiply these together. So that's 1x. But whatever operation is here, which is subtraction, you change it there. But the last one's always plus, and it's the last one squared. So 1 squared is 1. Now, a better way to write that would be x minus 1 times x squared. 1x is just x plus 1. And completely simplified. All right, next problem. The cubed root of 8k to the third. Does 125 divided by 8, is there a greatest common factor here? Let's try that out. So 125 divided by 8. Nope. Okay, I was just going to check just to be sure, so there's not a greatest common factor. But what I do know is that 8 is a perfect cube, and so is k to the third. Those go together because it's all multiplication. 2k is what that term is. The cubed root of 125 is 5, because 5 times 5 is 25 times 5 again is 125. And then we write down our formula. So it's the first one, keep the sign, and the cubed root of the last one. Then you have a longer set of parentheses, and you're supposed to square the first one. So when you square 2k, you got to square the 2 and the k. So 2 squared is 4, and k squared is just that, k squared. Now this is a minus sign. You got to do the opposite, so plus. You multiply these together. 2k times 5 is 10k, and then the last one squared is plus 25. Completely factored. Okay, let's change colors and do this again. All right, this one looks backwards, and you know what? That's perfectly fine if these are both perfect cubes. So 64, is it a perfect cube? Sure it is, because 4 times 4 times 4 is 64. 27a to the third, is it a perfect cube? Sure is. 3a. Now, when you write your small set and your big set, you keep this order. If 64 is first, then the cubed root of 64, which is 4, also comes first. And again, that means 3a comes next, and this is subtraction, so subtraction goes there. Then you square the first one. So 4 squared is 16. You change the sign to plus in this case. 4 times 3a is 12a, and then 3a all squared, got to square the 3 and the a, is plus 9a squared. And that is completely factored. Well, let's do a final page of problems before we wrap this up. And these might be weird ones, okay? So remember, the first thing we should always do is look for a greatest common factor. Well, on problem V, I don't see a greatest common factor. And I'm looking, and is that perfect squares, perfect cubes, what's going on? I do know that 64 is a perfect square, right? Because 8 times 8 is 64. And 64 is also a perfect cube, right? Because 4 times 4 is 16 times 4 is 64. Okay, interesting, isn't it? X to the 6th is a perfect cube, because if you have an exponent divisible by 3, that means it's a perfect cube, because the square root of x to the, the cube root of x to the 6th would be x squared. The reason, if you think about it, x squared times x squared times x squared is x to the 6th. And then 4 times 4 times 4 is 64. So let's look at this as a difference of cubes. So when I factor that, that'll be x squared minus 4 times, and then you square the first one in line, which is x to the 4th. You change the sign, you multiply those together, and you square the last one in line. Just like that. But now there's one more thing going on. This will factor again. That's a difference of squares. So that's x plus 2 times x minus 2 times all of this. That's an interesting problem. All right. Our next problem, 27k to the third x minus 8xy to the third. When I look at that, I see some greatest common factor going on. They both have x in them, so let's pull that out. I don't think I see anything else that's common, so let's just pull out an x. That's 27k to the third minus 8y to the third. And then I do my small set, my big set of parentheses. Don't forget about the x in front. It's still there. So there's my small set, and there's my big set. So the cubed root of 27k to the third is 3k, right? The cubed root of 8y to the third is 2y. Now think about it. 3k times 3k times 3k. Well, the 3 times 3 times 3 is 27. And the k times k times k is k to the third. Same thing here. 2y times 2y times 2y will definitely give you 8y to the third. So that means 3k, because it's subtraction, I put minus 2y. Then what goes over here is the first one, which is 3k squared. Square it all. That's 9k squared. Change the sign. Multiply them together. That would be 6ky. And square the last one. So 2y all squared is plus 4y squared. That is completely factored. And for our very last problem, is there a greatest common factor? I do see one. That y squared can come out. Okay, let's go leave me with x to the third, y to the third, plus 27. Now, is that, are those perfect cubes? Well, it sure is. What is the cube root of x to the third, y to the third? Well, that's xy. What's the cube root of 27? 3. So your greatest common factor has to stay in front, and there's your short set and your long set of parentheses. The cubed root of x to the third, y to the third, we talked about that, is xy. If you have a plus, you keep it a plus. The cubed root of 27 is 3. Now you're charged with squaring the first one in line. So xy squared, which would be xy times xy, is x squared y squared, plus turns to a minus. I multiply these together. That's 3xy. And I square the last one, plus 9. And I promised you these will not factor. So that is completely factored. I hope this helps.